Hello, everyone. Brilliant. Thanks. Excellent. Last time I spoke at SmashingConf, it was in New York, which I think was back in June, and I did this interactive game thing, right? And people were playing on their phones. There was questions, there was answers. There was like a scoreboard. There was prizes. It was a really good laugh. Exactly the kind of thing that you would want from the last talk of a conference. Good way to close things out, which I guess is why Vitaly put me in this slot. But that's not what I'm doing this time. I'm actually going to take a deep dive into internal browser behavior. In fact, at one point, I'm going to show you how standards are written. All right? We aren't going to be having fun. Like, just set expectations there. I'm not aiming for. At best, I'm hoping for. So just set expectations at that, yeah? But it's because of that, I'm like really stressed. I'm stressed that I've ruined Vitaly's plans for the conference. I'm stressed for Una because she's going to have to come on stage after this and sort of drag the whole conference out of this heavy technical ditch that I'm about to drive it into, and I'm worried she's run out of the jokes as well. And I don't know. Maybe it'll be okay. But I stress. I stress a lot. And I stress about things that aren't really problems. I stress about things that are really kind of nothing to do with me. A couple of weeks ago, someone posted this picture on Twitter. He's holding a MacBook with 2 fingers above concrete. I haven't slept since I seen this. I stress about code. I stress about code like this. Firstly, because there's no semicolons. Give me a cheer if you use semicolons in JavaScript. My people. The rest of you are monsters. But that's not the real reason this stresses me out, because it's adding an element to the DOM, right, and then hiding it, like presumably to show it sometime later, and that stresses me out. Like, can we be sure that the user isn't going to see like a flash of that element before it's hidden? Now, it's not something I've ever seen happen, but like, race conditions, right? You never know. You never know what's going to happen. So I will always just like swap those 2 lines around just so I could get some sleep that night, you know? But in reality, there is no race condition here. The timing of running code versus rendering is all tightly defined and mostly deterministic, and that is thanks to the event loop. And if I do a half-decent job in the next like 40, 45 minutes, you'll know why these things happen in the order that they do, and I don't know, it might even make sense, but no promises there. So, web pages have something that we tend to call the main thread. This is the main thread. We call it the main thread because a lot of stuff happens here. It's where JavaScript happens, it's where rendering happens, it's where the DOM lives. And this means that a bulk of your stuff running on your page has a deterministic order because it's all on the same thread. We don't get multiple bits of code trying to modify the same DOM at the same time, creating all kinds of race conditions. But it does mean that if something on this thread takes a long time, and by a long time I mean like 200 milliseconds, that's a long time for a processor, it becomes really noticeable because it's blocking a load of other stuff from happening. It's blocking rendering, it's blocking interaction. And I think it's difficult for us to empathize with this, because as humans we are extremely multi-threaded, right? I can stand here waving one hand, like standing on one leg, waving the other one, and all the time I am talking, I am taking in visual and audio information, all at the same time. As humans, we don't really have a main thread. We don't have things that block unrelated things, but we do have one, and it's when we sneeze. Because as you begin to sneeze, just everything starts shutting down. Like, you lose the ability to talk, that's the first one that goes. You pull a stupid face, that's the second thing. And if you're driving, when this is happening, this is the point where you get to think, I hope no one dies as a result of this, least of all me. The human body becomes entirely single-threaded. You are sneezing and nothing else. You can't see, hear, think. You can move and make noises, but only in ways that the sneeze wants you to. And then it's over, right? You essentially sort of wake up, and that is when you find out if your car is still on the road, if you still have the same number of limbs that you started with, the same number of passengers that you started with. Needless to say that we don't really want to write code that is like a sneeze. So although we have this main thread, we tend to spawn a whole series of threads for network stuff, for encoding and decoding, for crypto, for monitoring input devices. But once these threads have done something, like interesting, they've got a value, they've got something to report, they need to kind of get their information back onto the main thread. And it's the event loop that orchestrates all of this. So take this, set timeout. It's badly named, yes. The arguments are the wrong way around. Possibly, yes, I would agree with that. But you ever thought about how it actually works? Well, let's write a rough web standard for it, because that's what I do for fun these days. Here we go. The set timeout method, when invoked, must run the following steps. Wait ms milliseconds, invoke callback. Done. Excellent. OK. But spec text runs on the same thread as whatever invokes it. And in this case, it's being invoked by JavaScript. So when we say wait 5,000 milliseconds, we are blocking the main thread for 5,000 milliseconds. This spec is very sneezy. It's not what we want. So instead, we do this. We run the following steps in parallel. And this is magic spec text from the HTML spec that essentially says don't block. And the way browsers tend to implement this is they get off whatever thread they're on, which would be the main thread in this case. But we've created a new problem. We can't simply invoke a JavaScript callback from another thread, right? Like, else we'd end up with lots of JavaScript running in parallel on different threads, and that's not what we expect from stuff that's running on the page, accessing a single DOM. You'd be in a horrible world of race conditions. So we queue a task to get back onto the main thread at some point. And that ensures that we're calling JavaScript on the thread where JavaScript lives. And this is a core part of how the browser works. Like, how does a mouse click event get from the operating system into your JavaScript? Well, it queues a task. When you fetch something, how do you actually get the response data, the headers and stuff? Well, it queues a task. When you send a message from a page to a worker, how does that work? It queues a task. So the first part of the event loop we're going to look at are task queues. And rather than dive into the spec, because I think we've done enough of that for now, I'm going to try and visualize it. And there it is. That's the event loop, right? I hope this clears up any questions you had. I mean, I do hope it makes sense, actually, because I've kind of bet my whole talk on this diagram actually explaining things properly. So yeah, without anything to do, it just sort of whizzes round and round in a CPU-efficient manner, of course. Now, this visualization is running at a fraction of a % of real time, and it's still too fast, so we're going to slow things down a bit. When we queue a task, the event loop takes a detour. It goes over here. This is where tasks happen. So at some point, the browser says to the event loop, hey, I've got a job for you, and queues a task on the event loop, and the event loop's like, no problem, mate, sorted, done. And it gets executed, and that's it. But what if we have something like this? We've got these two set timeout callbacks. Well, according to our spec, those two algorithms go parallel. And they're going parallel for 1,000 milliseconds apiece, and then they each queue a task to get back on to the main thread. So in this model, the browser says to the event loop, hey, I've got something here that wants to do main thread work. Oh, actually, I have two things. This is one for each callback. The event loop is like, sure, just add them as separate items to the queue, and I'll execute them in the order that you gave them to me. So there's the first callback, and we go around the event loop, pick up the second one. Now, there's actually more than one task queue. Specs can define different queues for different things. So here are two queues, both containing 3 tasks. The event loop gets to pick any queue to take a task from each time. The loop guarantees that tasks within a particular queue will happen in order, but it doesn't guarantee which queue an item will be picked from each time. And this is to give the browser some leeway. It means the event loop can give priority to, say, a mouse click event over a set timeout if it wants, because they use different queues. So that's tasks, and it'll be pretty simple on their own, but we're going to take a look at the render steps. And this is what the browser uses to update what's on the screen. The render steps are another detour. They're over here, and this is, Emily was talking about this before. This is where computing styles lives, like figuring out which styles apply to which element, creating a render tree and performing layout, figuring out where things will appear on the page and what size they are. Then creating pixel data, the actual painting of stuff. Now, at some point, the browser will say to the event loop, we need to update something on the screen. So, can you deal with that? And the event loop's like, no problem, I'm on it. And it goes around that part of the loop. Now, I don't know about you, but I'm an expert at coding badly. I often end up creating these infinite loops by accident all the time. It's something I always have to debug. But what actually happens when we do that? Well, let's take a closer look. So if I have a page with a GIF and like some text on it and a big button which runs an infinite JavaScript loop, if I press that button, everything stops. Like the GIF has stopped updating. I can't select text anymore. It's all locked up. And the code for this is simple. It is just on click will do while true. That's it. Look, normally when I do this, it's more complicated than that, right? Like this is just an example. I think I would catch that one in advance. So what's actually happening here? We can show this in terms of the event loop. The user clicks a button, the browser says, hey, event loop, I've got this task for you to do. And the event was like, cool, whatever, I'm on it. But that task never ends. It's running JavaScript forever. And a couple of milliseconds later, the browser says, hey, event loop, we need to update that GIF on the screen, so can you like render as soon as possible? And the event loop's like, well, yeah, sure, I'll get around to it. Right after I finish this infinite loop, right? I'll be right on it. And then the user tries to highlight text, and that involves things like hit testing. It involves looking up DOM elements. So the browser says, I've got a couple of more items for your to-do list there. And the event loop's like, mate, are you taking the piss? Like, do you know how long it takes to perform an infinite loop? There is a clue in the name. It's a long time. So that's why a while loop blocks rendering. And it's a good thing in practice. Like, this is the code we looked at earlier. I used to worry that this would result in a flash of content, but it can't because script runs as part of a task, and it must run to completion before the browser can get round to those render steps. The event loop guarantees your task will complete before rendering happens. Still stresses me out. I will still flip those lines around, though, if I see things like that. So a while loop blocks rendering, but what about this? So this is a function that calls itself, but via setTimeout, something that queues tasks. Well, let's find out. Same example again. Click the button, and nothing appears to have happened. Everything's still working. But something has happened. So let's run that loop. So the browser's like, got a task for you. The event loop's fine, whatever, I'll run that. But as part of that task, it queues another task. It's like, OK, right, we'll go around and run the next task. No problem. On and on until the end of time itself. But as we've already seen, only one task can be processed at a time. It has to go all the way around the loop to process the next item. And that means that the browser says, oh, we should update the display. The event loop's like, fine, I'll do that. And there it goes. And this is why a setTimeout loop isn't render blocking. But if you want to run code that has anything to do with rendering, a task is really the wrong place to do it. As you can see, like tasks are kind of on the other side of the world to rendering according to the event loop. What we want to do is we want to run code in the render steps themselves, around about here. And the browser gives us a way to do that. And this is using requestAnimationFrame, another badly named function. You're welcome. RAF callbacks, they always happen as part of the render steps. So to show why this is useful, let's animate a box. Just a box. Here's the code. I'm going to move that box forward 1 pixel, then requestAnimationFrame. I'll do it again, and again, and again. And there it goes. Yeah, thank you. Excellent. RequestAnimationFrame, ladies and gentlemen. Right. But what if it did the same thing, but instead of requestAnimationFrame, we used setTimeout? Well, that's different. It looks like this. The box is moving faster, around about 3.5 times faster, I'd say. That means the callback is being called more often, and that is not a good thing. We saw earlier that rendering can happen between tasks. Like here we go, task, and we'll go and render, fine. But just because it can does not mean it must. So in reality, the event loop can do a task and go, shall I render? No, can't be bothered. Let's go and pick up another task. Right, should we render this time? Nah, maybe next time, off we go. Many tasks can be executed before the browser goes, yeah, OK, I will render and update the display. Now, the browser gets to decide when to render. It tries to be as efficient as possible. The render steps only happen if there's something to update. If nothing's changed, it won't bother. If the browser tab isn't visible, it won't bother. But also, the majority of screens update at a set frequency. As Emily was talking about this earlier, it's mostly 60 times a second, and that's why 60 frames a second is our goal. But some screens run faster, some screens run slower. This screen runs at 30 hertz, so like 30 frames a second is the target because it's as fast as it can do. But 60 hertz is the most common. If we change the page styles like 1,000 times a second, it's not going to render 1,000 times a second. It's going to synchronize itself with the display and only render up to a frequency that the display is capable of, and usually 60 times a second. And that makes sense, because otherwise it would be a waste of time. There's no point in rendering things the user will never see. But that is what set timeout is doing here. The box is moving faster because it's updating the position of that box more times than the user will see, more times than this display is capable of displaying. And also, so far, we've been using this like set timeout thing to kind of mean queue a task. It's not that pure, unfortunately. It's still, even though we're saying 0 milliseconds, it still waits a bit. It seems to be around about 4.7 seconds, but according to the spec, browsers can pick any number they want to sort of round up to. That just seems to be what Chrome and Firefox and Safari do. There isn't just a simple method to queue a task. I guess set immediate was sort of that, but we don't have that. But you can sort of emulate it using like message channels. If you create a message channel and post from one channel to the other, it always queues a task to do that. So that's the closest thing to queuing a task. And if we use that, and if you're sensitive to flashing images, you might want to look away now, because that looks like this. Tasks are happening so frequently, it looks like the box is just getting a random position. We're getting a task every 200th of a millisecond on this machine. So rendering can happen between tasks. We've seen that. But you can have many, even thousands of tasks between renderings. OK, flashing images are gone now. Right, imagine each of these is a frame that gets displayed to the user. The render steps happen right at the start of the frame, and that's style calculation, layout, and paint. I like this. It's very neat and tidy. I like it. Tasks, on the other hand, couldn't give a shit. There's higgledy-piggledy all over the place. Like the event loop does, it guarantees order of things within a particular task queue, but in terms of the timing within a frame, they do not care. And we saw this with set timeout before, right? Like we're getting 4 of these per frame, 3 or 4 of these per frame, meaning 3/4 of them wasted effort in terms of rendering. Now, some old animation libraries used to do this, so they're calling set timeout, and this number here is like 16.7 milliseconds, roughly. So the aim is to try and do that 60 times a second. It's assuming the screen is 60 hertz, but like I said, that's true in most cases. So that eliminates some of the duplicate work, fine. But it is a total hack. Set timeout wasn't designed for animation, and it does show. So due to inaccuracies, you can end up with drift, where, like in this situation, we've missed a frame, and we've done twice as much work in the frame after, which is pointless. And that causes visual jank. Also, if one of your tasks runs long, it can end up sort of getting in the way of the render steps as well, like spoiling their lovely routine, which is very rude. If we use request animation frame, this would look a lot more like this. So everything all nice and ordered and neat and tidy, and I like it. Even this expensive bit of JavaScript over here is well within the timing of a frame. I like seeing performance traces like this. Makes me feel nice and calm. Of course, you cannot avoid tasks completely. Most events are delivered in tasks, not all, but most of them. So if the user clicks somewhere, you kind of want to act on that straight away, and that will be in a task. But if you have things like timers, if you have things like things arriving from the network, it's worth using request animation frame to sort of schedule and debounce that stuff to batch it together, especially if you already have animations running, and this will kind of save you a lot of CPU time. I treat tasks like I treat people who drink fizzy water. I acknowledge that they exist, but I do not trust them. Like I would consider myself a person like quite empathetic, maybe, I don't know, but I do have my limits. I think soda water is vile, and I believe it's impossible for a human to drink it without gagging and throwing up. So the people who do drink it, something else is going on there. I maintain a Twitter list of people who drink soda water. It's not a creepy thing. I'm just keeping my eye on them. But when I find the link between these people and Brexit and Donald Trump, I am blowing the case wide open. There's a link. There's got to be. And it pains me to tell you this, SmashingConf, but this conspiracy goes straight to the top. Yeah, also watch out for that guy. Where is he? Plotting. Every now and then, some smart ass will say to me, but Jake, you drink Diet Coke, and I think you'll find the main ingredient of that is fizzy water. No, that's different. It's completely different. The main ingredient of air is nitrogen, right? But let's see how long you'd last breathing just that. Totally different. Anyway, that's request animation frame. Oh, actually, before we move on, there's one detail that catches most developers out, and it's caught me out as well. Request animation frame happens before processing CSS and before painting. So code like this might seem expensive, like looks like we're doing loads of stuff, but as we saw earlier, like JavaScript will always run to completion before rendering happens. So in this case, the browser just sits back and lets you have your fun changing one value back and forward. It doesn't really think about the result of any of this until the style computation parts of the render steps, and that's when it goes, all right, what did you actually do there? And the only bit that matters is this last line. Cool. And this explains a gotcha in CSS, or something I certainly ran into. You might run into it as well. I had a thing on a page, and when a user clicked a button, I wanted to animate that thing from an X position of 1,000 to 500. Sounds like it should be easy, but it's the web. So I had my listener, and I set the transform to 1,000, start position, fine. Set a transition, because I want to transition it, and then I changed the value to 500. But that animated from 0 to 500. And I was like, no, Mr. Browser, that is not what I asked you to do. I clearly said 1,000 to 500 and not 0 to 500. But the reason is the same, right? It's setting these things, and it's just sitting back and letting me set values over and over again and ignoring me. So the first value where I set 1,000, it effectively ignores it. The start position is overwritten before the browser thinks about styles. Anyway, I figured that out, and I thought, right, we'll fix that. And I wrapped a second bit in request animation frame, and there we go. And now, it still animates from 0 to 500. It's still broken. What is going on? I will tell you what is going on, because I figured it out after reading the spec. So the user clicks on the button. So we queued a task. Fine. The event loop comes around, starts running that task. And this is where we set that initial transform and the transition. And then we queue a request animation frame, so around we go. And this is where we set the final position. But the browser doesn't think about styles until the block that comes next, the purple block of the S in. That's where it calculates style changes. So again, just like the previous example, it's losing that first value before it ever thinks about it. And that's why you need not 1, but 2 request animation frames if you want that thing to correctly animate from 1,000 to 500. This ensures the browser calculates the style of the start position, and then later calculates the end position in 2 separate style calculations. There is a hacky alternative to this. We can use getComputerStyle and read the transform property. And this forces the browser to perform a style calculation a lot earlier than it naturally should, but it makes it take note of that start position, and this works fine. But like Emily said before, you need to be careful if you're forcing the browser to do these things earlier than it naturally would. This isn't layout thrashing as such, because by accessing getComputerStyle, we're only asking it to compute styles, not layout. So it's a little bit cheaper than that, but you can still run into the same problems. The correct answer, the easiest way to actually do this would be the Web Animation API, but it's only in Chrome, so yeah, whatever. It's not a great answer for real world yet. So if that was a surprise to you, this positioning of request animation frame, do not feel bad, because Edge and Safari get this part of the event loop very wrong. They process RAF like here, in the wrong place. And that means when you get a click event or whatever, or something in a task, and you queue an animation callback to change some stuff, Edge and Safari will update the display before running your callback. So if you're trying to make rendering changes, the user will not see them until the frame after that one. And it's, reasonably significant delay depending on the screen. And it's a real pain in the arse when it comes to trying to defer stuff to like the rendering steps, because it's going to put that extra frame in the middle that you don't really want. So that's Edge and Safari. I hope it's something they fix soon. Chrome and Firefox, they do it in the right place according to the spec. Right, that's enough about request animation frame, but I wanted to address a little bit of a lie that I told earlier in the talk. We're going to have a look at the compositor. You see, earlier I said that an infinite loop blocks rendering, and that is kind of true. But here's another example, very similar to the one before, but there's a little bit of extra movement in that GIF. I click the button, the GIF stops, I can't interact with the page, but it's still doing that little animation. what's going on? Something non-standard is going on, but it is something all browsers do, so probably something we should look at standardizing. Although the render steps are in charge of style calculation, layout, and paint, it isn't the thing that actually puts the pixels on the screen. That is down to this. This is the compositor thread. It is also synced to the display, like the render steps are, so it'll kind of run at 60 Hertz on that kind of screen. Let's take a closer look. So, when the browser comes around to do some painting, and this is where it creates all of the pixel data. But like I say, it doesn't put that straight on the display. It actually uploads that to the compositor thread as a texture. And there it goes. And the compositor takes all the pixel data as it receives, and it arranges them into a page, and that's what gets outputted. And this is where things like scroll position are taken into account. So it's got all the textures, and it goes, oh, but the scroll position's at 50, so I'll slide that stuff up by 50 pixels. And that's how that works. But in particular situations, it can do something pretty cool. Like if during style calculation here, it sees a declarative animation, by which I mean a CSS animation, a CSS transition, or a web animation API animation. Basically any kind of animation where it knows the start and end in advance. It can look at it and go, huh, this whole thing can just be done on the compositor. So it uploads a program to the compositor, and off we go. It can control the rest of the animation. And it only works if it's the kind of animation that the compositor can handle on its own. The compositor, like once again, like Emily was saying, it can't draw. It can only take already drawn bitmaps and move them around. But that worked in this particular situation. Like instead of drawing this as just one image, it draws it as two. And now it can move those things around independently. And not just position, they can be rotated, like even in 3D. It can also change opacity, like perform particular filter effects, some of the mixed blend mode stuff. That can be done here. Certain kinds of clipping as well. It's something Safari is really good at, and I wish your browsers were as good as Safari in that respect. So what browsers can do on the compositor is a little bit different per browser, but like opacity and the transform sort of filter as well, I think are pretty common across all the browsers. Anyway, we didn't do anything in 3D. We just like did a little rotation on that image, and yes, all of that can be done on the compositor. So when the user clicks that button, we queue a task, and yes, it contains an infinite loop, so the event loop is blocked. It can't update the frame of that GIF anymore, because that's a paint action. It needs to upload the next frame. It can't handle user interaction, because that involves the DOM, and that's all blocked. But the compositor keeps on spinning, and it has the program for doing that little rotation animation, so that's why it can continue. Yeah, and that's why particular animations aren't blocked by JavaScript. And it's certainly something we recommend, that if you're using things like transform, you use transform rather than top and left, because that can be uploaded to the compositor, and it won't be janked by things running on the main event loop. OK, that's enough about rendering for now. It is time to have a look at microtasks. Probably the least understood part of the event loop, I'd say. I pretty strongly associate microtasks with promises, but that is not where they started. Back in the 1990s, browsers wanted to give developers a way to monitor the DOM, monitor changes in the DOM. So the W3C gave us mutation events. And this meant you could add a listener for something like this, like for when a node was inserted, among other things. But in practice, this was really problematic. Say we're going to add 100 spans to the body of the page like this. How many events would you expect from this? Like one event for the whole operation? 100, one for each span, yes. But also another 100, one for each text node being inserted into each span. And that's because these events bubble. Because of this, like relatively simple DOM modifications could trigger thousands of events. And if developers were doing some work in those listeners, it quickly became a whole bunch of work, and it became a real performance disaster. What we really needed is some way to have these things batched up and just be told about kind of sort of independent changes. And we've seen already the browser does this with style. Like we were able to change those values, and the browser just sat back and kind of paid attention to the overall change. We need something similar here, because this is just one piece of work. We only want one event, not 200. The answer became mutation observers rather than mutation listeners, and they created a new queue called the microtask queue. Most documentation I read about microtasks say it happens at the end of a task, or a turn of the event loop, which doesn't really mean anything. And it's kind of true. There is a point on here where microtasks are handled. It is just after a task. But that is not where you're likely to encounter them. Microtasks also happen when the JavaScript stack goes from being not empty to empty. So it's kind of whenever JavaScript finishes executing. So you can end up like running microtasks within a task. You can end up running them within the render steps as part of request animation frame or other events. Anywhere JavaScript can run. So that means that this JavaScript runs to completion, 100 spans and their content are added, and then once JavaScript's finished executing, it goes, some stuff has changed in the DOM, I will fire an event to deal with that. So promises, they also use microtasks. So here, a microtask is queued, fine, and then we log yo, and now the script is done. JavaScript stack has emptied, so we process those microtasks, and there we go. We call our promise callback and log hey. That means that when a promise callback is executing, you are guaranteed that no other JavaScript is halfway through executing, and that's one of the important reasons microtasks were used. You're kind of guaranteed that promise callback is at the very bottom of the JavaScript stack. But what happens if we create a microtask loop? We saw this with set timeout, we've done normal JavaScript. What about microtasks? Well, same test as before. Click the button, whole page freezes. It blocks rendering just the same as a while loop does. So sure, promise callbacks, they're async. But what does async actually mean, right? All it means is that it's going to happen after synchronously executing code. So in this case, yo is logged before hey. That makes it async. It doesn't mean it must yield to rendering or any other part of the event loop in particular. We've looked at 3 different queues so far: task queues, animation callback queue, that's for request animation frame, and now microtask queues. And just to make your lives fun, they each empty in a slightly different way. Okay, so like we've already seen, when it comes to tasks, we get to the task part of the event loop, and we process one item, and only one item. And if we queue another task as part of that, it goes to the end of the queue. Done. When we process animation callbacks, we process them all, except ones that were queued while we were processing animation callbacks. And otherwise animation wouldn't work. If you call request animation frame inside request animation frame, that should happen in the next frame. Microtasks, on the other hand, they are processed until completion, including any additional items that are added. So if you're adding items to the microtask queue as quickly as you are processing them, you are processing microtasks forever. The event loop can't continue until that queue has fully emptied. And that's why it blocks rendering. I get really excited about this stuff. Sorry if everyone's bored. I'm really excited about this. Like, I used to have a proper job. Like, I really did. Like this stuff, like the standard stuff, the open source conference speaking, this used to be my hobby. But then my hobby became my job, and now I have no hobbies. I am a boring person. So, I didn't actually notice this happening. I didn't notice it until I went for an eye test. Where I live in Haywards Heath, and the optician, just making small talk, just asked, and what are your hobbies? Oh shit! When did this happen? I can't say nothing. And I panicked, right? And I shit you not, I said, I play the piano. I don't play the piano. And now I was really stressed that she was going to say, well, that's great. We don't need the letters chart then. Here's some sheet music. Can you read the first 5 bars? What chord is this? Thankfully, she didn't. But I am terrified to go to my opticians now in case we, strike up some musician chat that I couldn't be part of. I don't know how I survive outside sometimes. Right, okay, I think you're ready for this next one. I occasionally run little JavaScript quizzes. Maybe that's my hobby. Nope, that's work too. Fuck, okay. Anyway, this is one of my favorite questions. We've got an event listener, and we're going to queue a microtask and just do a normal console log. But we have another listener on the same element doing the same thing. If the user clicks a button, what happens? Which order are those things logged? Well, our first listener executes, and that queues a microtask. Fine, okay. And then we go on to log listener 1. Done, okay. So that's our first answer. And most folks agree on this bit, but what next? A couple of weeks ago, I actually ran a Twitter poll on this, and 63% of people say that the next thing that will be logged is listener 2. 5% of people think nan is logged 3 times and then infinity. That's not the answer, but fair enough. But as you can see, thinking listener 2 is the common answer. It's the wrong answer. But if you thought that as well, then you were in very good company. That's what most people think. But no, because our listener has finished. We have gone from having something on the JavaScript stack to nothing on the JavaScript stack. So that means it is microtask time. So we go straight to the microtask, and we log microtask 1. And then we do the same for the second listener, right? And that works the same. So the order is listener 1, microtask 1, listener 2, microtask 2. But that is only if the user clicks the button. What if the button is clicked using JavaScript? Oh yes, it is different. Very different. For starters, our script is on the stack, right? Script is on the stack, and we call click. And that synchronously dispatches the event. Button.click or button.dispatch events, they work exactly the same. Anyway, and that means we're going to start with our first listener, so that's on the stack as well. We queue a microtask, excellent. We log listener 1, fine. And now it's microtask time. No, it is not microtask time because our JavaScript stack is not empty. Event listeners run synchronously. Our call to button.click has not yet returned. So no microtasks. We go on to the next listener, queue another microtask, and we log listener 2. And now our listener is done. In fact, all of our listeners are done. So button.click returns. And now our JavaScript stack has emptied. And now we can process those 2 microtasks, and they happen in order. So that small little difference has kind of changed the order. It's changed when promises run. And this has real-world practical implications. If you're using automated test frameworks, be careful if they're using JavaScript to click on things, because you'll start getting these differences showing up. And like I said, the same happens with manually dispatching events. So look for an automated test system that dispatches clicks at the operating system level, or uses something like Chrome DevTools protocol, so Puppeteer and all of that sort of stuff. They do the right thing here. They're doing real clicks. They don't have this problem. But another practical place where this came up is that we were looking at how to add observables to the DOM, and it's something we're still looking at. And we're also looking at how they integrate with promises. And we hit this question. So this is a promise for the next click on a particular element. And it's just a little bit of code. New promise, add event listener, click, and we'll resolve then. Fine. But the question we had is, can someone still call event.prevent default when they use this promise? Because promises are async, right? Have we missed our chance to prevent the default? Turns out, no, it's fine. It works. Not a problem. Unless, as before, the event is triggered with JavaScript and then it changes. And to figure this out, we really kind of need to look at the spec. This is a little bit simpler than the real spec, but it shows the problem. So this is what happens when a link is clicked. We create an event object, and then for each of our listeners of type click, we're going to invoke the callback with the event object. Fine. And then, if event object's cancelled flag is unset, we're going to follow that hyperlink. When you call event.prevent default, it sets the cancelled flag on the event object. That's how that works. So if the user clicks the link, this is fine. Our microtasks happen right here, after every callback. And that's before step 3. So if they call prevent default, that's fine. We'll pick that up, and we won't follow the hyperlink. But if we call click with JavaScript or dispatch event, it's just going to call straight to our other algorithm here. But the JavaScript stack is no longer empty, because that click method, it's synchronous. It's going to stay on the stack throughout the whole process. So we can't run those microtasks there anymore. They run much later, sometime after click returns. And that means step 3 is going to happen before any of our microtasks run, so the hyperlink is followed. And then sometime way later, our promise callbacks happen, and we try to call prevent default, and it just doesn't do anything. We've already followed the link by that point. So if you're trying to turn something synchronous to something asynchronous, do bear this in mind. Remember that microtasks only run when the JavaScript stack is empty. Right. OK, last thing I want to talk about. I want to talk about event loops. Now, some of you might be thinking, what exactly has he been talking about for the past 40 minutes, if not exactly that? Well, I have been talking about an event loop. But in reality, modern browsers have many, all doing their own independent thing. For instance, if you create any kind of worker, it gets its own event loop. That's how it doesn't jank the page. The browser UI usually runs on its own event loop. But what about multiple pages? You've got multiple tabs, multiple pages going on, and iframes and stuff. Like, what do they do in terms of event loops? Well, naturally, there is no straightforward answer here. Old browsers used to put all pages on the same event loop, including the browser UI itself. So here's an old version of Firefox showing 2 pages from completely different sites. Click the while true button, and both pages are locked up. In fact, the whole browser has locked up. I can't interact with any of the URI or the buttons or the URL bar or anything like that. And while I'm clicking around there, it's just adding things onto the task queue, the event loop. And what Firefox would do is eventually it would halt long-running script, and then that queue would start emptying again. So this would happen, like everything starts moving and reacting to all those clicks. When Chrome was released, it was the first browser to put tabs on different processes, therefore different event loops. So here's Chrome, click the button, that page freezes, fair enough, the other page still keeps on trucking, and the browser UI, that all works, it's not broken or anything. That was Chrome 1. Internet Explorer 8 kind of did it in some cases. Edge does a much better job. Safari 7 introduced the same thing, and Firefox was kind of the latecomer here. It introduced it just in November in Firefox 57. But the extent to how browsers do this, it varies. The only rule in the spec is that pages must share an event loop if they gain synchronous access to each other, or if they can gain synchronous access to each other. What does that actually mean? So here's 2 iframes. One is same origin, one is cross-origin. With the same origin iframe, I can get access to its window, its document. I can add stuff to the DOM. I can read stuff, call JavaScript. I can really do whatever I want. And this means the iframe must be on the same event loop as the parent. Otherwise, there'd be no way to do that kind of synchronous communication between the two. It would be just race conditions everywhere. But if I try and access the content of the other iframe, I get a big error. Right? It doesn't work. Because I shouldn't be able to read and modify the contents of your bank, you know. This means this iframe can have its own event loop. Though browsers are actually very good at doing that for iframes. It's something we're working on in Chrome. It's behind a flag. We're just fixing the final bugs around printing, it turns out. Same goes for window.open. Window.open works pretty much the same as iframes. But what if we have a link like this with target blank, so it's going to open in a new tab? Will the newly opened page get its own event loop? Well, let's test it. So I'm going to click the link here, opens in a new tab as expected, and I'm going to click that button. Now this has locked up both pages. So in this case, they are on the same event loop. And it has to do this according to the spec. Now, when you open a page this way, your page doesn't get access to the page it opened. There's no way to do that. But the new page does have access to the parent using window.opener. And that represents the window that opened this one. And because the 2 pages are on the same origin, the child can synchronously access the parent and do whatever it wants. The same as iframes before. What about this case? Same URL, roughly the same link, click the button. This time it only locks itself up. It doesn't affect the other page. The parent page continues to work. The only difference in that second case is that link use rel equals no opener. And that means that opener is null on the other page. There's no way for the 2 pages to get synchronous scripting access to each other, so they don't need to be on the same event loop, and that's why one page doesn't disrupt the other. And it is optional for browsers to do that, but it is something that Chrome and Edge do. It will sometimes work in Firefox. Firefox will have a maximum of 4 event loops for pages, and it just kind of distributes them evenly. That's kind of a way that they save memory. We prefer to try and use a different event loop as much as possible for kind of security isolation reasons. In Safari, it doesn't make a difference. It'll still lock up the page. But it's an optimization they can make. That said, it is important to use no opener even for cross-origin sites. Like if you're linking to another origin, it can't do this because it's another origin, right? It can't start messing around with the page. But it can write to the location object and navigate the parent page. And this will change the URL bar of the page and everything. It will do a full navigation. But if the user's clicked on the link and they've opened a new page and they've gone around, and that page has secretly navigated the parent page to a different URL, but it looks the same as your bank or whatever, can you be sure that the user will catch that? Can you be sure they'll realize that that page could navigate the other one? And that's why we recommend using no opener on all external links, especially if they open a new window. Okay, that was a massive brain dump of pretty much everything I know about the event loop, about all the various steps and various queues that there are. And knowing this stuff, going through the spec on this has really reduced the number of times that I've needed to throw a set timeout around like something just to kind of fix a bug. and even then it only fixed it intermittently. It's helped me avoid jank by getting stuff kind of running only once per frame rather than multiple times per frame. And I hope I've managed to explain it in a way that was useful to you too. Like I said, I'm a stressful person, so I'm going to go and collapse somewhere now. But you've been a great audience. I've really, really enjoyed this conference. Thanks to all the other speakers. Thank you very much. Cheers.
I'm sorry to be the bearer of bad news, but you can't collapse yet.
Oh,
Join me in the chair.
I tried to run long, so I avoided this.
I'm just going to ask some really light questions.
All right.
A little late, and I was so mesmerized by your slides that I just didn't even
take in any of the information. That's what I was aiming for. Yeah.
They were so good. How did you make the slides? How long did they take you?
It was a couple of weeks of tinkering and stuff.
Okay.
Yeah. It was time. It was time.
Yeah.
I was enjoying myself. It was the first time I'd kind of done a lot of manual stuff with SVG and stuff. So
Very
it was really
cool.
good fun. It was good
And
fun.
what Jake didn't mention is that last slide with all the circles, which kind of remained throughout, was generated in random circles. Can you talk about that more? It's really cool.
The code is terrible because it's one of those things like, I've got to give a talk. I probably shouldn't spend 3 days trying to get one animation, unimportant animation working. Yeah, it was just an SVG circle with a little dot on it. And it was just, but then it was animating the SVG element itself because that goes onto the compositor thread. So it would just pick random places to see where and it would grow the circle until it touched another circle or reached some kind of maximum size. And then it just kept doing that until, because it was like a minimum size of it. If the circle couldn't get beyond a certain size, it didn't bother. And then when it tried to place 100 circles and didn't manage that 100 times in a row, it would just stop. And that was it. So it's terrible.
It looked nice while we saw it.
Yeah, it blocks the main thread for 200 milliseconds. But the great thing is, the end of the previous slide is normally static, so you don't notice. It's great. Yeah, it's cheating.
Yeah.
Fantastic.
Speaking of bad performance. So you showed this slide with all of these different animation loops on a page. That probably wouldn't be the best thing, right? In Firefox, it can only have 4 max. So what would you recommend to make this a more performant experience?
What for what particular kind of animation? What for like?
Using animation loops or even multiple animation loops on a page.
It should be fine. Like the thing to avoid is having layout thrashing. Like if you're avoiding layout thrashing, you're doing the best thing. Yeah, because you need those multiple callbacks. There's not a whole lot of benefit of merging those multiple callbacks into one, unless it's to avoid layout thrashing. I kind of wish that we had a system where we had a callback for after render. I've got a thing in the HTML GitHub thing to kind of say, like, can we have a callback just straight after paint? So we can have one place where we do all of the reads. Like, I've thrown all the styles at the thing. It's rendered. Now give me a point where I can kind of read the position of everything ready for the next frame. And having that sort of regimented way of doing that will hopefully prevent like layout thrashing.
Totally.
Maybe.
Have you seen any really good examples of web animation in the wild lately that use some of these techniques, like maybe microtask or something else that you brought up?
I mean, mixing animation and microtasks it wouldn't be usual. I mean, there's the web animation API has promises built into it, so you're kind of using microtasks there by default. But the only case you would really use microtasks is if you're wanting to batch work together. So I know React uses microtasks, so that if you update state multiple times, it doesn't update rendering multiple times. It uses a microtask to let you sort of finish your work and then do it. But that's not animation specific. No, so I guess my answer is no.
Okay. But that's interesting to note that React uses microtasks. The last question is just a really general one. And it's, what are you most excited about these days? Like, what's new, shiny, and wonderful in the web for web performance or web animation?
For web animation, it's the animation worklet. So this is a way that you can run some degree of code on the compositor thread. So like that sort of, with CS animations, you can do like a bit of a rotation or something. But if you wanted to link animation to like the scroll position or do some more complicated stuff, like if you were doing an animation that you wanted it to sort of bounce, do a bounce effect, there isn't a way to do that using like the cubic Bezier easing stuff. So yeah, this worklet that will run on a composite thread would be a way of doing that. So that one of the examples we have is that when you're scrolling on Twitter and the avatar sort of gets smaller and then sort of locks to the top, you could do that there, and you're not running that on the main page, so it's out of the way of other JavaScript that's running. I think we're getting close to a spec on that. It was so the Chrome team kind of wanted to just let people do JavaScript, any JavaScript they want on the compositor. The Safari team were like, no, we don't want that. We want just like some kind of declarative CSS thing. So it's kind of being a meeting in the middle where it's sort of partly declarative, partly imperative. A lot of stuff is set up in advance, like the timings and stuff. But per frame, you can decide the position of particular textures that are being composited.
Okay.
So I'm excited about that.
Yeah. So is there a timeline for it? Is it still in early stages?
Oh, now you see, it's not the thing I work on, so not my department, mate.
Yeah. Not my problem.
If we haven't got something in Canary already, we've got Paint Worklet is in Canary now, or it might even be heading towards stable. Animation Worklet, I think we've got stuff in Canary, but I don't think it's not ready for prime time yet.
Yeah.
They're still figuring out parts of the spec.
So just look out for it.
Yeah, maybe this year, maybe, I don't know.
Yeah, cool. Thank you so much. That was an amazing talk. Give it up for Jake one more time.
Thank you very much.
Cheers.